Okay, welcome back to the second half of this class. I understand that this is a bit dry. It's about going through the mechanics of coding in Mathematica, but the principle is general. So, you'll be able to use it in all kinds of language. But at the same time, there are some very special function that I like to highlight that I find very useful in practice. Okay, so basically I can give you example of univariate or multivariate function call, right? But the one that I chose here are the one that I think are not only interesting, some of them are interesting, like, factor integer, for example, that's interesting on its own, but certainly the useful one, okay? The one that's used all the time. Table, for example, is used all the time, okay? Another one which I use pretty much everywhere is a function called thread. You guys know what the threading is? It's like how you sew things, right? You thread like needles, okay? It's a little bit like that. What this function does is it's kind of like a template function. What it says is that give me a list of two things, okay? Two lists of things, okay? So it could be a list of 7 numbers and 7 integers, or 7 colors and 7 animal names or something. It doesn't matter, okay? The point is that these two lists are of the same length. So there's like a one-to-one correspondence, okay? And the thread is you can do any kind of function pairwise, one at a time. All right. So you think of like a piece of cloth on the left-hand side, a piece of cloth on the right-hand side, right? When you kind of like sew the piece of cloth, you kind of like go back and forth between the right hand and the left hand. Well, think of right hand being a list of things, the left hand being another list of things, and thread being some function that links the element pairwise. A good example would be, and this is how I created this, okay? So you don't have to look at, so I format this so it looks nice. X is a list of 3 things called A1, A2, and A3. Okay, I created it with table or just enumerated, right? Y is a list of 3 things, B1, B2, B3. Now think of X1, X2, X3, B1, B2, B3, and think of a function that couples X element and Y element together one at a time and go down the list. That's called threading. So if I do this, literally, I type in thread X, comma, Y, and I put a bracket around it. What it's going to do is go to element by element and repeat that instruction, put a comma, put the left side, put the right side, put another bracket, go down the list. So if I have a list of X and I have a list of Y, and I want a list of a pair of X and Y, I would just say thread X pair with Y. Does that make any sense? Okay. Right. So in high school, some high school have like a homecoming dance, right? Boys stand on one side, girls stand on the other side. The first boy dance with the first girl, second boy dance with the second girl, in which case the function would be X, thread X, dance Y. Okay, so that would take the first one in the X row, the first one in the Y row, and they dance together. Second one in the X row, second one in the Y row, dance together. Okay, so what's thread X plus Y? Well, again, it's going the first element of X, A1, first element of Y, add them, go down the list. What's thread X divided by Y? I can do with anything. Okay, now I can even do symbolically. X point to Y thread. If I want to thread X point to Y, that means each element of X point to each element of Y, and that's my new list. So it's creating a list of some kind of operation between individual elements. Okay. Does that make sense, guy? Okay. By the way, if I have a list X and Y, put them together and I transpose, I'll get the same thing as the first one. Okay. Anyway, don't worry about it. Now, okay, fine. In Mathematica, in Python, once you learn how to do assignment, once you learn how to do list, what's the next most useful data structure in Python? Dictionary, DICT, right? Well, dictionary technically is an association. So Mathematica, well, they both technical definition. Association is what Mathematica calls dictionary in Python, or Python calls Mathematica. Okay. So association is an association of same thing, a list of thing and a list of thing, except it's a special relationship. The first list of thing is a list of key. Second list of thing is a list of values, so that when you go to the key, it points to the value. Does that make sense? Right? So this exactly is what I mean by association. Okay? Association, okay, is like a list, except each element is some kind of pointing between key and value. So it's a key value list. Okay. Now, that in itself, if I just put a bracket, it would be a list of A point to B. Association, by definition, and this is the only thing you need to remember. In Mathematica, association uses this kind of funny bracket. Okay. So this funny bracket, say, this is the key. If the key is the letter R, the value is red. So I'm going to name this thing. RGB association. Okay. Okay. I'm going to call this RGB association. Okay. But how do you key in right angle? Just say minus greater than, and it's going to combine to. Okay. So type in exactly this. Okay. RGB or whatever. So equal to funny bracket. So that's less than straight up. So this is the funny bracket. Inside, make this tree association. Okay. Ready? Shift enter. So now, if I say, oops. So now, if I say G, which is a key, it's going to go to a value. Okay. Right. So basically, this is creating a one-to-one. Okay. One-to-one mapping. It doesn't have to be one-to-one. It could be many-to-one, because everything can point to the same color. But to make it useful, basically it goes like this. So you don't want to do this. You don't want B to go to green. So what you want to do is this. This is bad. I don't want this. Oops. Okay. So this is a dictionary or association. It's designated with a funny bracket and an arrow. Okay. So once you have this, these guys R, G, and B, these are the keys. These are the values. So now, if I say, what is the keys? So once again, let's not cut this, okay? So that's my association, right? My association. If I want to call blue, I just put in B, okay? Now, if I want to know, once I build the list, I want to know what are the keys. I put the function keys to it, right? What are the keys? That's my keys. What are the values? Okay, right? So basically, I created this. I could create this using thread. So again, thread These are the most powerful things I use programmatically. Okay. So again, this guy, thread, it's a wonderful function. I use it all the time. Okay. Associate thread. Association is a data structure I use all the time. And so association thread, obviously, is also a function. So this is what I do. Okay. This function, I don't think I have it here. Okay. Association thread. Okay. What do you think happened? So this is what okay. Son, daughter. Okay. And let's give them name. Okay. So son. Okay. So my kids equal to this. So now my kid, let's say I've gone see now. I don't know what my son's name is. Okay. So this is kind of like a thread, but it's a thread that creates combination. So, okay. So this is the same thing as a thread of, and then put a association on top of it. So this is the same thing. Okay. So this is to turn a list of this thing point to that thing. Okay, let's do this one at a time. Okay, let's do this. Right? So the first element point to the first element, second element point to the second element. But notice it has a regular bracket. So to turn it into a funny bracket, I have to make it into association. Okay. And now my kids, well, I don't know, daughter. Okay. This is used all the time in data science or data analytics. Okay. So now you've got the thread is just a useful hack, but association is used all the time. See, Alice is sad, Bob is so and so, and blah, blah, blah. Okay. Right. So that's it. Now, let's start thinking. Okay. Let's start thinking. Now, we haven't gone to machine learning yet, but believe me, this is exactly how we're going to format our machine learning. One of the way that we can format the data is what? Think about it. Well, forget supervised learning. Let's think of regression. Regression equation, you've done that, right? Y is equal to f of x. Well, instead of saying y is equal to f of x, can you say this? I want an association for every x value, give me a y value, right? It's the same thing as regression line, right? Give me an x, I multiply by the slope, add the intercept, that's the y estimate, right? So that's exactly what it is. X is the key, y is the value. So XY pair, in a way, is basically a list of pointing thing, right? So you can think of it as association. So this pointing thing, by the way, will be the way we format IO or input output, X to Y. Okay, but I'll come back to it. So anyway, so okay, a good example would be this. Okay, this is an example. You don't have to type this in. Okay, just wait for your book to see. Okay, so this is my data. Okay, my data is a list of 1, 2, 3, 4, 5, 6 people, right? So 6 row, right? 3 column. The first column is weight, I guess, right? In kilograms, say. And the second is height in meter. And the third one is sex. There you go. Okay. Right. Now, these are people with names, but I don't care about names now. I care about whether or not they are diabetics. So imagine that, let's say diabetic, you can predict, okay? You can't, but let's for this example, let's try to predict whether or not the person is diabetes by studying the past data that comprises of the height, the weight, the sex, and whether or not the person is diabetic. So you can think of the list of height, weight, and sex as the input. And the list of status, yes, diabetic, no, not diabetic, or healthy, as a target, right? So this is it. This is your X, this is your Y. Diabetes IO is this. Okay. This is exactly what you would feed into a machine learning algorithm. This will be the format. Remember it for the rest of your life at least. Okay, so that is, see, 71 kilogram, 1.7 meter male is healthy. That's data point number one. 71 kilogram, 1.2 centimeter male is diabetic. Oh, exact same measurement, but one's diabetes. See, it's not, data is not, it's like this. That's a real world data, right? Same measurement. So one guy is diabetic, the other guy is not. Okay, fine. Okay. So that would be my data. This is exactly how data analytics gets format. Okay. So association thread just does that very easily. Okay. Right. This is some kind of BMI level function. Okay, don't worry about this. Okay, I define this as a function. This is a user-defined function. You don't know how it's done yet, but I define it. Okay, there you go. I take the same thing as before, but instead of looking at the diabetes or not diabetic, I look at the first two numbers and I calculate the ratio and I check whether or not it's above certain threshold and I evaluate as healthy or overweight. Okay, so I do this. Okay, so this is an association. This is an if-then rule. Okay, why do I show you this? Why I show you this? This is exactly how people try to build AI in the early 70s. In the early 70s, they tried to build AI based on if and then, if rule. If this ratio is between here and there, say something. If then, if then, if then, if then. And medical diagnostic with AI in the 70s looks a little bit like this. And in fact, medical AI in a lot of cases for screening still works like this. If your blood sugar is above 6, accumulated blood sugar above 6.0 in 2 consecutive months, and you are over 30 years old, you are diabetic, something like that. Okay, so it's this diagnostic medicine with AI, quote unquote, very old-fashioned AI, 1970s AI work exactly like this. Well, not exactly like this, but in this spirit. Okay, so these are 2.18. These are considered useful, meaning that we can come back to this. Counts, that's a good one. Counts just give you a count. Okay, I have a whole bunch of things and I just count them. Okay, how do you read this? How do you read this? I give you a list and it gives you a count. 1 has 5. There are 2 7. There are 5 3. There are 3 4. There's 1 5. Okay, these are all very useful functions. Okay, you will use this in data mining in lecture 2 lectures from now. Okay, map is also a useful function. This will come back. I think what I like you to do is once you get the book, try to type in this yourself and see how it matches with the explanation. This is also useful. It's basically just to add member to a list, then join. Okay. Replace, this is also good. Sometimes you have a thing and you have a rule. If I see A, replace it with 1. If I see B, replace it with 2. Okay. String count, that's also, useful. So these are all useful. Okay. So what have you learned? The primitives, assignment, list, function. Function, you have seen function that cannot take an argument. I call it a prompt tomorrow. A function that may take 0 argument, like what's the current time? Okay. Function that takes 1 argument, function that takes 2, function that takes 1 or 2 or 3. Okay. Now, when you have options of taking 1 or 2 or 3, what it means is that it actually takes 3. And when you supply with 1, they just set the rest to default. Okay. So you know how to work with function. Okay. Later on, you're going to find out that, hey, the function, the 3,000, 5,000 function that's built in is not good enough for my purpose. Okay. You're not doing anything complicated, but you're doing something in the step that is not there. For example, adding is not complicated. Multiplying is not complicated, but you want to add and then multiply and then come back to add. For some reason, you want to do something like that. Okay. That's part of your accounting program. Okay. So you're going to define your own function, right? You're going to define your own function. Okay. Now, function that you define, there are 2 functions. Okay, 2 ways. Okay, forget this, skip, come there. Okay. There are 2 ways you can define a function. Okay. I'll teach you I'll show you this kind of weird function definition first. What it means is that it's called a pure function. A pure function is not given a name. Why would you want to define a function and not give it a name? Well, sometimes you want to do something somewhat trivial. You want to do it just once. And you don't want to name it. Okay? For example, right now, I just want to take the first element and raise to the power of second element plus 5. Okay? I just want to do this. Okay? I just want to do this. And I want to do this for a whole bunch of things. I would not want to name this. These are called pure function. Okay? So we'll come back to this. The reason I haven't shown you now because it looks a little bit weird. Well, I can show you what it does. Okay? What it does is a sort of like monkey show, monkey do kind of thing, right? Take A multiplied by this thing, add B, apply it to 5. So you put 5 in there and you get 5A plus B. So it's a little bit awkward. Okay, all this a little bit weird, but it's just sort of like show me what to do kind of thing. Don't follow this. This is gonna be like very obscure looking thing. Okay, this is where, and this is unfortunate that when you go to a user group in whatever language, people like to show off how good they are with programming by writing everything in shortcut. Well, this is kind of like a very shortcut way of expressing things. So you see this kind of hash thing all the time in a user group, just to show off. But actually, it's not just for show off. It's literally very efficient way of programming. Okay, but not now, not today. Let's go to today. And now with this, you can literally do all kind of stuff. This is called defining your own function. By the way, do click into this. Okay. This is called pattern matching. Okay. And you can remember, type this, by the way, type this. My function, okay, it's blue because it's not defined. Okay, let me do it one at a time. write this line, my f, just my f, okay? Okay, my f, open bracket. Now, underscore here is used for pattern matching. What it means is that I want to do a function on A and B, but it's a pattern matching A and B. In other words, in the future, anything can come in this place. So this is like a placeholder. Okay, and this is this is the most fundamental way of functional programming. Okay, you define a function this way. My function takes on, in this case, how many argument? How many argument? 2. So it's a multivariate function I'm defining. What is the first argument called? I'm going to call it A for now. I underscore. So when you type, you will notice that the first A looks like this, right? When you put underscore, it gets a green color. Oops. Okay. Let me show you. Okay. Right now, blue doesn't know what it is. Open bracket, purple doesn't know what it is. Blue doesn't know what it is. Now I put underscore, comma. Okay. And all this. And eventually, whoops, sorry, A with an underscore becomes green. That is a notation for saying it's a placeholder. Anything I put in here, I'm going to call A. Anything I put in here, I'm going to call B. What do I do with A and B? I do this. Okay. It's like an assignment, but it has a colon before it. Okay. Just memorize this. In fact, this would work as well, but there's some technical reason why you should do this. It has to do with order of computation. Don't worry about it. Just do this forever. You will not go wrong. Okay. So define my function, blue. I don't know what it is. You haven't defined it. Have two placeholders, a place called A and a place called B. And I'm going to do this, A and B. Okay. Now shift enter. Now notice this blue is no longer blue because now it's defined, right? In fact, if you type in my, it's going to autocorrect because now it's registered. See that? Once you define it, it's just as good as a built-in function. Okay? It becomes autocorrect. Okay? Auto suggest, sorry. Okay? So now if I put in some number, 1, 2, 3, 4, 5, 6, 3, 4, 5, it's going to say, aha, I'm going to put this here in this place, which is here. I'm going to put this here in this place, which is there. And there it is. Okay. Now, if for whatever reason you need multiple steps, and in fact, in definition, sometimes you're going to need a lot of steps. You're going to have something like a something something, and then another something something, and then this. Okay. And then this will be the result. Okay. So this could be 100 lines. Okay. But right now, it's just a one-liner. So I don't need to put the list. Okay. But the lists are separated by a semicolon. So basically, this is the instruction. Whatever comes here, I will identify it as A. Whatever comes here, I will identify it as B, and I will perform this to it and give you the result. That's how you define the user function, user-defined function. And now, if you use this a lot, it's convenient. Okay? Convenient. Okay? Watch this. And this is a little bit too early, but I'll show you. It's a shorthand. Okay. Well, I'll just do this. Let's say I have a list of A and B, C and D, E and F. Right? Okay. Nah, never mind, never mind. Let's do this. No. Okay. I'll come back. I'll come back to this. Anyway, okay. Right. You have this thing. Okay. You have this thing. Now, what if you want to have like intermediate step? Okay. For example, let's say you want to have an intermediate step. You don't want this. You want something like, well, this same thing, I want to make it an intermediate step, just for fun, okay? Temporally, temp measure is equal to e to the b, okay? And then a plus temp. Okay, just type along. Okay. Now, if I did this, okay, same as before, let's call this F2. Okay, I'm going to get exactly the same thing. Right? Okay. Now, if I want this thing, okay, I'm trying to do something here. Okay, so you get this. Okay, fine. The point is that you can have many lines in here and you can create a temporary variable. What happened here is that when you did this, one thing happened. You create a global variable called temp. So once I've used this, I've long forgotten that I use it. I type in temp. It's still going to keep this. This is very messy. Okay, this is very messy. So there's one construction that I want you to get into the habit. It looks a little bit complicated, but once you get the hang of it, it's not. Okay, what you do is instead of defining this like this, you use the word module. Okay, module has two parts. The first part is the list of local variable. Second part is whatever you want to do. Okay. Okay, that's the difference. Now let's say let me clear temp. Okay, so now you don't know what temp is, right? Right? If I use this function, okay, my F2 1 2 3 4 comma 5 6 7 8, okay, I get the same thing, right? But look what happened. In the process of doing this, I created a temp variable, but after I use it, temp still not defined. Why? Because by putting it inside this construction called module, this temp becomes local. So that explains the color green. See, normally when I make an assignment, right? When I make an assignment and it becomes something that's known as black, okay? Now it remains green. Why? Because it's local. Create a temporary variable, do something to it, use it. Once this function is exit, it's gone. Okay. This is the way to do function definition. Okay. So, obviously, of one line of function, there's no temporary, right? But anytime you create like an intermediate step and you have to do this kind of calculation and you want to do something in between and have this variable use it, you don't want it to be created and last forever. You want it to be used within the function and dies within the function. Okay. So this is the way of. So I want you to memorize all kind of thing. First of all, define a function with a placeholder with colon equal, and then this module, right? Module has two components. The first component is a list of things. So maybe you have two things. You can have temp1 and then temp2. Okay. Temp1 is equal to, you can do this, B, and temp2 is equal to E to the temp1. Okay. Temp1, 1. And then you can have temp3. And then you can say temp3 equal to A plus temp2. Now, obviously, you can do all this in one line. And then you can return temp3. Okay. So this is a very convoluted way of doing exactly as before. Okay. So this module creates a whole bunch of things. This is all temporary. Does this, do this, do this, do this. Okay, this is one instruction, one line. This is like a separate line. Okay, that's it. You've learned everything in terms of programmatic. Okay, now, okay, so you will see that for the rest of the book, the textbook, when I define any kind of major function, I would do this. This is a good one. Okay, signal to noise. Signal to noise. For example, signal to noise is a very, this is a stupid way of doing this because you can do this in one line. But watch this, guys. Signal to noise is a function. Okay. Have I defined it? I define it. Now it's black. X. X here, I expect a series of number. Okay. I create temporary variable. 5 of them, in fact. 5 of them. The first one is equal to length of X. Why do I do that? Because I want to know how long it is, right? How long it is, fine. Mean is mean of X, obviously. Mean standard deviation minus standard deviation. So mean minus X minus mean square, variance is total. This is all like one line, okay? But I'm just drawing it out. So I'm doing very tedious calculation. The point is that at the end, I get mean divided by standard deviation. Okay? So I apply this to this, I'm going to get 1.36. Okay? Right? So this sort of thing, well, then I cleaned it up. Good. Function shorthand, I think you saw this before. A plus equal to 9, Now, this is the most important shorthand. Okay? It's saying apply F. Remember this one? Yeah. Exponential A, right? You guys remember this? right? Univariate function, okay? What's the shorthand for it? Apply to A, all right? Okay, now if I want to apply to a list of A, not to the whole list, but to an individual element, this is what I do. Apply to a list of things, A, B, C. Okay. That is the most useful programmatic hack there is. Basically, that's list comprehension in a very, very precise way, right? I think I don't remember. I haven't programmed Python for a while, but I think it's something like for something like exp of I for I in A, B, C, or something like that. I think list comprehension. Okay, it's a bit clumsy. Okay, but here it's very shorthand. It's just saying this is the action you want to do. I want to do it not to just one guy, but to a list of guys. This is a shorthand for the word map. Okay. So map X, map this function to this, to this, to this. Okay. Except you will never see this in real life code because, you know, this is actually more intuitive. Sometimes you see this because the list is a little bit nested and it's complicated, and that's advanced. Okay. I'll show you, because you can actually apply to different level. You can have lists of lists, and you don't want to apply exponential to the top list. You want to apply exponential to the element within the list, or you want to apply to the element within an element within an element of list. So you can specify the level. So that's the complicated, but for a straightforward one level list, okay, not list of lists, this is it. Okay, you will see this all the time in my note. Okay, my note. Okay, ready? And now, now I'm gonna introduce you to this guy. Okay, let's say I have a list of things, A, B, C, right? I want to do something to it once, just once. So I don't want to name it. Okay, right now, let's say I have this. Let's say I have my function. Okay, my other function, my F3 of X is equal to, okay, 1 plus X squared. Can I do that? Can I do that? Yes, I can, right? I just did. Right? So I define this function. So I call this function to A, 1 plus A squared. Now, whatever I want to apply to A, B, and C, how do I do this? Okay. So now type this. I define this function. I use this function one at a time to all the element in the list. That's it. Okay. Imagine that you need to do all kind of data manipulation. And this is where data scientists become very boring and tedious. You have to do a lot of formatting and cleaning, all that stuff. If you did this and you only use it once, you can have F3, F4, F5, F6. Okay. Now, instead of defining a function and name it, I'm going to use pure function. A pure function just tells me takes 1 plus whatever it is, square it, Okay. And to denote, and this is the only thing you need to realize, add the ampersand. This ampersand, say anything in front of it is a pure function. So basically it's the same function as that, except I don't use X as a variable. I don't name it my F. Does that make sense to you? Yeah. So this is a function. This is a legit function. You don't believe me? I put A on it. See? Same thing, right? So my F3 times apply to A, get that. Same here. Except here, I went through the trouble of naming it. So this is kind of unnamed function. It's called pure function. Okay. It's a pattern matching thing, right? Without a placeholder. It's just saying, hey, whatever you see here, put in the hashtag and do this. Does that make sense? Okay. Now, this is what you'll see me do all the time. Right? Why? Because this is a list of things. I want to do relatively simple operation once. Okay. And this happens in a lot of data science projects because sometimes you just need to do some kind of formatting, some kind of cleaning, some kind of unit conversion. Okay. So these are things that are, I really don't need to show you this, but the reason I show you this is because I think of this as a hack. If you are comfortable with this syntax, which doesn't look nice, I admit. Okay. And the first time I got into programming, I see a lot of this. I was very annoyed. Okay. And I kind of thought all these users in the community, they just try to show off and they know a lot of shortcut, right? Well, it turns out that when I start to program a lot, this becomes a very good hack, very handy hack. So this does what? You should be able to answer that. Okay. What does it do? Well, the first thing is, because you see this ampersand, you know it is a pure function. That pure function just does whatever it says over here. Okay, let's do something else. Let's say this function is log of x to the cube. Okay, right? It's saying that this is a pure function. Whatever I see, I put it in here. Now, I don't want to do it once. I want to do it to all the element of the list. Right? And now you have all the hacks you need, I think. Yeah. This is another one, but it's not as common, so I'm going to forget it. This is not map. This is called apply. I don't use it that much. Again, I'm a little bit biased, okay? Replace is used a lot. So all these are in your book. And so this is shorthand for apply. This is shorthand for this and blah, blah, blah. But replace all is used a lot. So take the list, replace with the rule. Okay. String join, that's used a lot. Okay. Now, are you guys done? Yes, you're done. This thing here is called, oh, by the way, in Python, pure function is called alpha, right? Any of you done that? Alpha function in Python? No? I think it's called that. Let me check. alpha function. No, sorry. Okay, we have to edit this out. It's lambda. Have you done lambda function in Python? Okay, lambda is a pure function. Okay. So instead of using the word lambda, you just use an ampersand. Okay. So the two correspondence for those of you who are familiar with it's Python lambda function, not alpha function. Okay, fine. Lambda function. Right. Now, this thing about association, key and values, right? If you think about it, if you work with heavy duty data set, raise your hand if you heard of pandas. Okay, pandas, if you think about it, it's a table, right? But it has a built-in functionality for fetching element, for comparing, for count if and all that kind of stuff, right? So what is pandas? Okay, let's go back a little bit. Well, for those of you who didn't come from programming background, are you familiar with Excel or spreadsheet? Right? Okay. Imagine you want to do spreadsheet, but you want to do it programmatically. Why? Why would you want to do it programmatically? Because some data is so big. If you load into an Excel sheet, it will hang, right? And yet you want to do something relatively simple like find or multiply column A with column B and divide by column C. You want to do something very simple, right? But if you were to do it, or you want to group by, for example, you have country, you have geography, or you have male and female and college student and undergraduate student, and you want to find the means of male as opposed to mean of everyone. So group by male category and take an average height. Group by female category, take an average height, something like that, right? Can you do that in Excel? Yes, of course, right? You can sort it by male and female, right? And then you can take the average of just the male column or take the average just the female column. Okay. First of all, drag and drop is tedious if you have to do millions of rows. In fact, you can't do millions of rows because it won't load, right? So to do it programmatically, all the functionalities you would like to do in Excel, you have to do in a data frame. Okay. Pandas is the way Python is a barebone language. It doesn't have data frame. So pandas is a library on top of Python that gives you data frame. Okay. Well, in Mathematica, data frame is called data set. That's all I want to say. Okay. So it's a little bit more, it's standardized. So it's like this, instead of having a table, you can do this and you can do group by, exactly the same thing, all kind of that data manipulation. Now, I'm not going to go into that today, this thing about data frame or data set. Why? Well, because it's a whole 3 hours by itself, okay? And second of all, until you get to the real data, you won't need to do that yet. But when you get to the real data, trust me, real data, you cannot do any data science project on Python without pandas. Likewise, a lot of time in Mathematica, you would prefer to use data frame. Data set, not data frame. Okay. The word is data set. So, look it up, data set. Okay. Okay. So data set it's much nicer. It does all this group by thing and all kind of things. Right. Now, last thing, well, not last thing, near the end, you have to import and export from the data file, right? So this is what import export does. Okay. Okay. So far, let's stop here. Well, the class hasn't stopped, but I'm going to make an underline here. So far, everything you've done conceivably you can do in Python. Okay. Next one, not so sure. There's a SymPy that does a few things, but I just want to show you, this is symbolic computation. So I think I challenge some of you to do this kind of like, I think there was a student who came with, try to do this. Yeah, let's try to do this. See if you can do this with SymPy. Okay. What it does is, you know, do this expression in I going from 0 to infinity. Now, I chose this one specifically because it looks terrible. It looks terrible. But you know what is it? Do you know what it is? It's actually sine x. Okay. See if you can do that in SymPy. I think there was one guy who knew how to do SymPy. Okay. So this requires summation. It requires factorial function. It requires symbolically going to infinity. It requires a test of infinite series. Yeah. So try that. Sine, cosine. This is also good. Comes up to, so all this identity. This is a fun one. This is a double summation. J from 1 to I from 1 to infinity. Okay. Now, I chose this specific one because these are well known to have a very nice expression. Okay. But very clever. So this is also, oh, how about this? This is a product, guys. It's not an infinite sum. It's an infinite product. Okay. Now, I want you to try to do this yourself. Except, do you know how to do this? Well, this is actually a product, right? So there is a function called product, but you might as well do this. Since we're doing mathematics, go to Math Assistant, right? Math Assistant allows you to enter all this function in mathematical form. Okay, so this is actually a library called a function called product, but or multiply, I think it was. But here, see, you can do this summation. Where's the summation? Yeah, there it is. So this is a product. So can you find this? Yeah, enter the product and then basically do this. Okay. So see if you can do this. Okay. Now, some of this, or this is also, you know, infinity. Okay. Some of this is not that useful or relevant to data science, but something like this certainly is. You know why? Anybody? That's how you find probability, right? Integrate PDF. Okay. Ball wine into all kind of stuff, that. So you know, this is like a show off, you know, to say, you know, again, very, very advanced stuff. Have I actually used this? Yes, I have. Yes, I have. I will tell you later, but maybe I'll tell you now. You guys done statistics, right? You know what a correlation is? I hope, at least. Well, a generalization of a correlation function is called a copula. A copula. Okay? A copula is a general way of computing relationship between two things. Okay? I was working for the Bank of Thailand, so I was working with financial problem. In the financial market, it became known, especially after the financial crisis of 2008, that the correlation was the wrong way of measuring dependency. Okay, what I said, it's not exactly accurate, but roughly speaking, they use what's called Gaussian copula. Roughly speaking, it's the parameter of a correlation. Basically, they use the wrong copula. By using the wrong copula, they underestimate the risk. And by underestimating the risk, they were taking on risky position that they could not cover. By taking on risky position they could not cover, and they cannot pass on to the market, banks fail. In particular, Lehman Brothers is no more. Okay, I'm not saying that Lehman Brothers went bankrupt because they chose the wrong copula, but it was one of the major reasons that you unveil the story of why Lehman Brothers failed. You say, oh, you see words like CDO, collateral debt obligation. You see something about CDO pricing model, default correlation. You dig it down, you get to Gaussian copula, you dig it down, that's the wrong copula. Okay, so definitely this is real thing. This is real thing. Now, when I was at the Bank of Thailand, I was trying to invent a new copula that measures the correlation relationship. And that requires me to do some kind of fancy integration from minus infinity to plus infinity. I could not do it. So that's why I came back to Mathematica. I didn't even use Mathematica for my PhD thesis. Okay. Okay. In fact, I use C++ for my entire PhD. I used very tiny bit of Mathematica, and I never thought I needed it. It's only when I literally could not do anything because this integral was just staring in front of me and there's no way I can do it. And I needed to do something fancy like these. Okay. That, yep. Does it work? Good. Good. Very good. This one too? Yeah. Well, I can give you the one that I'm pretty sure Simpai would not get, and that's the integral that I needed for my copula. Okay, it ended up doing yeah, it's just good fun. I'll talk to you later. It comes up with a semi-analytical solution, but this is good. So it does double product. Okay, does it? Infinite product. It does infinite product. Okay, cool. Okay, so I think it's caught up. Certainly, when I was doing this, there is nothing else. Yeah. Okay, expand first order, fifth order polynomial. So you can expand, you can find polynomial. These are all kind of computation that some of it are needed. Okay, now, and this I'm pretty sure that this can be done in Python or MATLAB. This is solving system of equation, but doing it symbolically. For example, this is a 2x4 matrix, so that's 2x2 matrix. That's easy to solve. Okay, so that's the solving thing. What was trying to do? Yeah, I did some kind of analytical solution. So PDF, all kind of things. This is, yeah. Finally, let me just show semi-analytical computation engine, which means that, you know how a ratio should not be solved numerically until you get to the final ratio, and then 1 divided by 3 is 0.33, right? Likewise, you should never do things numerically if you can do it symbolically. Okay, so you should do things symbolically, analytically, but sometimes you need to go semi-analytical solution, and that's where you do things like DSolve. Okay, this is I'm just going to run too quick because this is not that relevant to, but it's in the textbook. Okay, this is an equation. You guys know what this is, right? Anybody has a friend in engineering? You know what a partial differential equation is, right? Okay, well, U is a heat function. U is a heat function, right? If you have a metal rod, right? U is heat as a function of position X. time t. Okay, so x is position of a length of rod, let's say. That's as simple as it gets, okay? And then t is time, all right? The idea here is that change in temperature as a function of time, partial with respect to t. Okay, let's make this really big. Partial with respect to t is proportional. I'm just putting 1/7 just for fun, okay? But basically it's proportional to second partial derivative with respect to position. So in other words, if you are here, that's your position, to your right and to your left, if the temperature gradient is sharp, so you take the second derivative and there's a big difference between you and next to you, then you cool down fast. Okay, that's what it means. Okay, if you're hot and right to your right and to your left, you have a high curvature to a very cool friend. Okay, you're hot-headed, your friend is cool-headed, you will cool down quick. That's what this means. Okay, so change in temperature with respect to time is proportional to the curvature of the heat difference across space. I don't know if I say it right, but it's something like that. Okay, well, I call this my heat equation. And then I set my boundary condition. My boundary condition is that partial with respect to x, okay? As x go to 0 and x go to 1, meaning at the beginning of the rod and the end of the rod is cold. So I have ice here and I have ice here and I have cool rod. Okay, so I call this. I don't have to name it, but I name it so it's easier. Okay, notice I put this equality twice, so it's a mathematical equality check. So I call this heat equation, I call this boundary equation, and I call it initial condition. Initial condition is like initial heat distribution. Now I do solve heat equation subject to boundary condition and solve for this. Okay, now I put timing around this because it's going to take, last time it took my very fast machine 31 seconds. This is probably going to take 2 minutes. But anyway, so that's input number 432. So the output hasn't come up yet. But you can see from the output that hasn't been deleted. This is the solution. It's equal to 22 divided by 12 plus 2 times sum to infinity of k, 1 minus k to the pi cosine. This is it. Okay. Try this also in SimPy. I don't think you can do it. You can do this numerically. You can do this numerically in MATLAB, I think. MATLAB, okay. But this is actually giving you a the reason it's called semi-analytical is because it has infinite series. So you can't stop. You have to keep adding, but the term gets smaller and smaller. So anyway, so that's going to take a long while, guys. So I'm not going to wait for it. And basically, I can simplify it to this. So that's the solution. And then I can store this solution as my heat solution, and then I can plot it. Okay. So that's it. That's basically. So this is okay. You guys know what this is? Well, see that this is my rod. At 0, I put it in an ice. At 1, I put in ice, so temperature is 0 here. There's initial temperature, very hot in the middle. There's a temperature gradient. There's a difference, right? And because of this, it cools down. Now, this doesn't look that impressive, but this is common sense, right? If you have something very hot in the middle, and at the end, it must go to 0, right? What happened? Well, the 0 heats up and the hot thing cools down. So this thing cools down, this thing heats up. Okay, right? Because I only set 0 at the beginning. Okay, at the end, it doesn't have to be 0. Okay, so in the beginning, I have 0, 0, and heat. And I let it cool as a function of time, and I get this. And this is semi-analytical. This is not numerical. With MATLAB, you can do this numerically. evaluate each point. Okay, so that's basically it. The hot thing cools down, the cool thing heats up and gets to an average temperature. Okay. And so let's clear that. Good. And that's sort of like where we are, is the end. Okay. Now, okay. So today it's a mix of two things. It's a mix of language primitives and function and, you know, syntax, but it's also an introduction to some of the quote unquote little hacks that I myself fell in love with, like thread. Association thread is a beautiful function. I use it all the time. Pure function, I use it all the time. Mapping / add, I use it all the time. Okay, those are not quote unquote lecture 1 of mathematical programming, but I squeeze them in here because trust me, when you deal with a lot of data, those are so nice to have, right? So it's sort of like yeah, it's practical in the sense it's formal in the sense that I'm teaching you the language primitive, like teaching you a language, but it's also practical because in my experience of doing this for many years, these are things that are useful, right? Association, thread, all kind of stuff. Now, if you are going on to say health and well-being or sustainability, you may want to use Mathematica to prototype your application. Again, you can put this on cloud and show it. And once again, if you're going to start working with data in any meaningful sort of way, which is why you're taking this class, presumably, right? These basic hacks will become very useful. This, you know, pure function, I don't need to tell you. I didn't need to teach you, but I did because it's going to come in very handy. Okay. Now, the same lesson applies to other language, except the equivalent of pure function here, you will have to find it somewhere else. In Java, I have no idea what it's called. In Python, it's called lambda. Association in Java, I don't know what it's called. In Python, it's called dictionary. This table construction, I don't know what it's called in Java, but in Python, it will be list comprehension. Okay. Again, these are all very useful hacks. Not really hacks. It's almost like a basic tool of the trades. Okay. It's like, please learn this early. Okay. Even though it's not elementary programming 101. Okay. And it looks a little bit like a, yeah, pure function looks very advanced because it's kind of symbolic functional programming, but it is so useful. Okay. So when you get the book, which I hope will be tomorrow afternoon, bear in mind that the function I use to illustrate function, univariate function, multivariate function, list construction, the one that I selected because in my experience, these guys are really good to learn. Okay. So these are like, maybe there are more things that are very useful. I just haven't used them that much. Okay. So this could be personal bias. I'm sorry, but, you know, you're learning from me, so you're learning from my experience. Okay. So it's a experience as a professional. I was not a professional programmer, right? But I did a lot of data analytics in various projects, a lot of it in finance and risk management, but also in non-banking application. Okay. So this, so if you see this function that I picked them here, just trust me that, yeah, they're good to learn. They're good to learn. Okay. And finally, the last part, which is the symbolic, that's a little bit advanced. That's just to show you that really this is a lot more powerful than you are using. And if you're at the frontier of cracking the functional form, like I was trying to create a brand new copula that has never been used before. And I couldn't do it myself because, you know, I didn't have the advanced mathematics to do that. I rely on the analytical engine. So it's a little bit like this, okay? It's a bit like this. I can, one of the example, a useful example is partial differential equation that was used by researcher in the 70s to price financial derivative, ended up winning them the you know, Nobel Prize. Even though the math itself is simple, the idea that you see this math problem in finance, that was not trivial. That was very advanced thinking. But once the advanced thinking was done, the equation was very simple. It looked a bit like this. In fact, and I'm not lying to you, literally, the equation that three people Nobel Prize, okay, Black-Scholes and Merton, the equation, the math equation was this one. This thing that you saw called heat equation. It was that genius to solve heat equation in financial derivative. But once they saw that, solving was simple. It's like literally like this. Literally like this. Except, here, let me show you. Let me show you. You guys see this? U of X is a heat, right? Let's go to this one. Now, I may be saying something. Come on. There. There. Right here. Literally, this was a function that won the Nobel Prize. It's so simple, but it's the fact that in that application, you know what U is? U is an arbitrage-free price of financial derivative. T, same as here, is time. X is actually the underlying price of the stock. So you have an underlying price of stock, let's say, you know, some share, Apple, IBM, I don't care. And you have financial derivative called options, which is very simple. It's the right to buy certain share at certain price, certain moment in time in the future. X is a price of IBM or stock index or something, underlying random variable. And U is the derivative written on that. This pricing equation for the first time coupled the derivative price with the underlying price mathematically. And this was the Nobel Prize. Okay, it's pretty cool. I actually use it as a story called innovation, like 300 years in the making. I don't know if some of you may or may not have attended the summer class I did last year. This summer I didn't teach, but summer last year I did. And how this thing started out as a botanist named Brown. A botanist is a guy who studies plants. He takes a glass of water, drops a pollen, you know, a pollen is, right? It's a thing inside the flower, and it moves. That movement is called Brownian motion. That randomness, Einstein put a mathematical equation on it. That mathematical equation then was used a few years later to link another thing that moves. So now you have a random thing. You have a things that link to random thing. Okay, so that was like, if this changed, how would this change? So that's done by Japanese mathematician in the 50s. Then in the 70s, it was used so that the first thing that wiggle is not pollen in a glass of water, but the price of a stock in a share, in a stock market. And the second thing was a derivative. And this thing became heat equation. And the solution to that won them the Nobel Prize. That's a pretty cool story. That story is 300 years old. Well, 200, I think Brown, I'm not sure how old Brown was, but Victorian botanist. So that, yeah, 300 years. So this involved botanist by the name of Brown, Le Bachelier, who is a mathematician in Paris, Albert Einstein, who puts this heat equation, Professor Ito from Japan, who does this kind of chain rule between this thing that wiggle with that thing that wiggle, and then Black, Shaw, and Merton, who put this onto a financial problem and won themselves Nobel Prize. That's a pretty cool story. Anyway, so that's just something that not everybody know. It's a little bit of a fun thing. Okay, I want you to, again, I'll give you Dimuti will give you 5-10 minutes, right, to send what you wrote down today. That will be like in-class work. You'll get your book hopefully tomorrow afternoon, but definitely Thursday. Okay, go through this. Try to key in as much as you can. Okay, try to key in as much as you can. You don't have to turn them in, but it's for your own good. And just trust me, if I select the function like thread or association or data set, these are good stuff. Okay, and how would you learn about it? You just press F1. But there's a lot more learning resource. What I'm going to do now is, when next class comes, we are going to start to dig deep into data analytics proper, starting with interactive visualization. Okay, by then you will have known enough about, by now, you know enough about built-in function, user-defined function. So we'll just start using that. Okay, and that will be chapter 3. Okay, so chapter 3 is about interactive visualization. It's about saying that if you've got the data and you plot them right, you get the insight right away. No AI needed. Okay, no machine learning needed. No probability model needed. No statistical estimation needed. You get the data, you plot them right, you get the insight. Okay, that's interactive visualization. Then you go to things where you need probability, you need machine learning. The thing is, once you've done all that, how are you going to present your result? You come back to interactive visualization, right? So next week is a very crucial week. Okay, so let me say that again. Interactive visualization is an end in itself, because sometimes you get your data, you plot it right, you show the right graph, you get the insight. If not, by plotting the graph, investigating, visualizing the data, it helps you build machine learning algorithm. It helps you build probability model. It helps you build supervised learning approach. Once you build that, you're going to visualize the result. You come back to interactive visualization again anyway. So the interactive visualization is not just window dressing. It's not just creating PowerPoint. Okay, it's going to be crucial to your career. Okay, because at the end of the day, that's how you communicate your result. Okay, that's how you communicate your result. It turns out, and I cannot underline this enough, you can spend months doing very hard data science, probabilistic modeling, machine building, machine learning, all stuff. When you present your result, it comes down to, you know, that interactive visualization, whether or not your client's going to buy it. It's sad, but it's true. It's sad, but it's true. Okay, so that is like, you know, you do a lot of work, 3 months, 4 months, 5 months, and then it's 2 hours of interactive visualization that say whether or not your project is going to pass. And that's reality. Anyway, I'll see you guys next week. Okay, I'll give you guys 5 minutes, 10 minutes, whatever, to do this. Okay, Cap. Thank you.